Hi, my name is Serene Gould, and this is my presentation on differential equations as models of population growth. So the central idea is how can differential equations be used to model population growth? So consider this, there are approximately 7.6 billion people on the earth. Amazon CEO Jeff Bezos has a net worth of 132 billion. And although this means he does not have this money right in his hand as cash, he's able, hypothetically, to give each person in the world $15 and still have 17.2 billion remaining. What do you believe this says about the disparity of wealth among Earth's population? So what is a differential equation? So it's a mathematical equation that relates some function with its derivatives. Functions usually represent physical quantities. It represents the rate of change, and the equation defines a relationship between the two. They play a huge role in many areas such as physics, biology, engineering, and economics. So the types of differential equations. So here are three different types of differential equations, and although there are many types of differential equations, these are the two that are mainly focused on for population growth. So a differential equation is an ordinary differential equation if it has ordinary derivatives in it. So the example is the variable m times the derivative of the variable v divided by the derivative of the variable t, which equals f times the variable v t. And an equation is a partial differential equation if it has partial derivatives in it. So the linear differential equation, which you will see later in this presentation, is any differential equation that can be written in the following form. And as you can see here to the right, this is an example of a linear differential equation. And although it uses different variables, it is in the same form. So modeling population through differential equations. So use PT to represent a population in any given region at any time. Rate of change of population equals the rate at which the population enters the region, subtracted by the rate at which the population exits the region. So here, the population is still the derivative, the rate of change, and the ways in which a species enters the region are incorporated. The existing rate that is all the ways for a population to leave an area. And we can see an example of this would be population migration and birth rate entrance. So an example here is a butterfly population. So in 2 weeks' time, the population will triple, and it grows proportionally to the current population. So 15 butterflies, and 16 of them are consumed by birds, and the other 7 passed from natural causes. So a total of 23 dead. And we can see here, you can determine R, which is expressed as RP and is proportional to current population. And once we've taken into consider that the unit is in days, once we have calculated the initial condition, which is 0 days, and the condition for 14 days, 2 weeks is 300, we solve for R, and given R, we are able to plug this back into this formula, and we are able to solve for T, which is approximately 50 days until the population is eliminated, which is about 7.2 weeks. And we can see here to the right this negative curve, and at around 50 weeks, we see the population is no longer. So here we see birth rate entering, which is beta, and then we see population size, and then deaths, which is mu time, which mu is in the mean times population size. And we can write this as the derivative of the rate of change divided by the derivative of time, which gives us the rate of growth of the population. What's important to keep in mind is that the differential equation indicates that the size of the population is proportional to the rate of change of the population size. Here we see population theories, Malthus versus Boserup. So Malthus believed that if we do not check our population, a huge mass of the population will die from widespread disease, famine, or warfare. And we can see this in his graph where the Malthusian trap is when the food produced and the food required intersect, and the food produced is no longer enough to meet the food required to meet the population standards. We also see, and then Boserup believes that with the increasing population, it's more minds to contribute to the advancing technology, which will compensate for the food required. And so we can see here the exponential curve of the total population, as well as the food supply, which always meets demand. So limitations to differential equations, they're not always available, and they can't always be solved by numerical equations. And usually there's only one approximate solution to them. And they usually revolve around 2 areas. The solution has to be approximated and how much accuracy is needed. And these are important factors to keep in mind when considering using differential equations to model population growth. So to wrap up this presentation, so despite the limitations found when determining the validity of differential equations, they have been known and proven to be accurate in calculating population growth, as well as accuracy of laws and theorems. And using differential equations, we can model various types of statistics, especially population growth. And without these partial differential equations, solving problems that involve functions of several variables to several degrees, such as quantum physics, sound, heat, and electrodynamics, would not be possible. Thank you.